First of all, we're gonna open your eyes so you can see who you're gonna call if you wanna be free. GLOBEBUSTERS! 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 Who you gonna call? Who you gonna call? Who you gonna call? Yeah! GLOBEBUSTERS! GLOBEBUSTERS! GLOBEBUSTERS!
And welcome everybody to GLOBEBUSTERS.
We accept the reality of the world with which we're presented. It's as simple as that.
And welcome everybody to GLOBEBUSTERS, Season 9, Episode 19. It is time for Math is Not Reality. Hopefully the sound is working okay. I'm going to double check with everybody to make sure. Check out the chat real quick and just make sure we're on the up and up. I have a new mixer, and it's been giving me a little issue. I guess you could call it not the calm before the storm, but the storm before the calm, hopefully. And I want to make sure, can you hear me okay right now? Did you hear the intro okay? Is the sound good now? Does it need to be louder? Give me your feedback, please. YouTube chat. Jeran, you're a little quiet. Thank you. So I will turn this up. Let me get some more volume here. Give me 1 second. And I will turn it up. Let's go here. I think I can turn this actually up too. Let me see if this helps you. Okay, that might have increased it a little bit. Let's go to open this one. Your sound is a little low. Okay. Intro 5 by, my sound 3 by. All right, give me 1 second. Then we're going to bring in Alan and see if you can hear him well. But this is good. I was all set up to go for my own stream, but not for having somebody with me. So we'll see. Here we go. This is the one here. We're going to go properties. What is its level at? Oh, so it's already at 100. Okay. Intro is bumping. You need more. Okay. I'm going to add some gain. Give me a second. We got to go to here. What is, oh yeah, gate is something else. I don't want that. Here's the compressor amount, and then it's makeup gain. Let's go up with this one. Okay, how about that? Let me lower my volume a little bit myself here. Or that's just in my headphones. It's too loud. Over here. All right, how's that sound? Any better? Or no, let me go up a little bit higher. How about that? We'll put that there for a second, see how people think it is. Sounds good, Jeran. You on YouTube? Greetings, GLOBEBUSTERS. What's up? Eric, louder, please. Getting better. How are we? Aisling, what's up? Turn it up, Jeran. All right, well, where are we at now? Still low? Alan, how does that sound to you? Let's bring Alan on. Oops, what's going on here? Huh? All right, now we got another problem. Why does it say failed to detect my microphone on... now it's working. Okay. Let me bring Alan back on. Alan, can you hear me okay? You're on mute.
Yes, sir.
All right, how do I sound to you?
Loud and clear.
Okay. Can you guys hear him, please? Maybe a tad more. We'll see right now when we get... can you guys hear Alan okay? Alan, go ahead and say something. Tell people where they can find your channel, all that fun stuff. Could be more.
Yeah,
all right, I'll keep going.
I'm sorry, go ahead.
No, my problem is right now I got to figure out where you turn down my headphones. My headphones are way too loud. I could go louder on my voice, but it's going to blow my eardrums out. So you got to think about that. Anyway, okay, still could be louder. I'm going to work on that. Can you guys hear Alan? Alan's 4 by, so he could be a little bit louder. Let me turn him up. Go ahead, Alan. Keep talking.
All right, so my YouTube channel is at @space_audits. You can find me there. Lately, I've been covering the history of interferometry and the ether, which is the previous framework of interpretation for the behavior of light. So when you get into talking about relativistic effects and all these things, what they're really talking about is how light behaves under certain conditions or conditions that they think exist, right? So that's what they're talking about. So I've been going into the history of, the old stuff that we're not really thought about. And so you can find my playlist there on my channel. I have it neatly organized. So that's what's been going on my channel.
Okay, awesome. How about now the volume? I went up as high as I can on him. I don't know. GLOBEBUSTERS audio is fuzzy. That's the first time anybody said that. Sounds very amateurish. Thanks, Go Vegan Earth. Appreciate your input there. I'll get right on that. Much buenoer. Sounds good. Okay, both of us are clear now, supposedly. He's
Cool.
about 75%.
Nice.
All right.
Nice.
Sounds good. So yeah, Alan's with me. We don't have Zack today. Zack is doing something with Jeran, and Austin is still moving. So you just got us two today. We're gonna have Alan do a little presentation shortly, and then we'll take your calls the second half. Happy afternoon. What's up, guys? Good level. Sounds good. All right. I'm doing great. It's just very loud and tinny in my ear. What if I do this real quick? That's weird. Test. Any better? No, that's better. All right. Let's get rolling with the first order of business. If you guys remember, I know we've talked about it 3 weeks in a row. You're probably getting tired of it, but I do think it's going to be one of the larger evidences that we've seen, and we still need more people's help, especially if you're in the South. I know not many people are, but we could use a few more people in the South watching the sunset for the next couple of weeks. So if that's something you'd be interested in doing, please reach out on Telegram, t.me/Jeranism, and we will put you into the sun watching group. And all you need to do is basically film the sunset 1 day a week for the next couple weeks. And we are determining whether or not we are seeing what we think we are. And I think I found the mechanism. Alan, let me ask you this. Does the globe belief say that we are moving fastest in December? Isn't that the belief that they say?
Yeah, because we have to be catching up to the sun and all that, and we're slowing down as we're coming back around.
Yeah, it's like, aphelion, whatever. So, I mean, I'm guessing that even though we don't spin slower, so I don't know how because I'm always looking at what's their mechanism going to be? What are they going to say is the reason for this? Because it's certainly hidden from us. And if people don't know what I'm talking about, you should at this point, but I'll go ahead and just say it again. That right now, if you're in the North, which most of you are, if you were to start a time clock, the second that the sun hits or disappears, let's say it sets, and you can no longer see the actual sun. If you started your time clock then, and you stopped it when you no longer saw any light from the sun, you would have, let's say today, you'd come up with 1 hour and 5 minutes, okay? And then if you did it in a week, since we're heading for December, meaning that days are getting shorter, well, that number is going to keep decreasing. So week by week, it may only be 2 to 3 minutes a week. So, next week you would do it again, and you would get 1 hour and 2 minutes after sunset, and then you would get 56 minutes, and then you would get, so on and so forth. And if that's the case, that means that our, light is diminishing after sunset in the North. And what the globe would call for is the opposite to be happening in the South, meaning that while we're losing light, they're gaining it. But that's not what's happening. We're finding out that everybody on Earth experiences the same results, the same effect, meaning that as we go towards December, we are losing time after the sun sets until there's no light, meaning that light is diminishing. And so is the South. So even though it's their summer, and you would think that their days are getting longer, which is true, then you would think that the amount of time after the sun sets that you would still see light would also be in turn, basically doing the opposite of what's happening here, but it's not. Everybody on Earth is experiencing the same thing, which is exactly what the flat Earth would call for. A flat Earth would call for a sun going about, this is going to be an estimate, 900 miles per hour. Do you know what the circumference of the Tropic of Cancer is? 20,000? It's a guess. I think it's about 20,000, but let me see here if that's correct. Just want to see what that speed would be. So if we go 20,000 divided by 24, 833. So the estimate would be that the sun ranges from 833 miles per hour to about 1,400 miles per hour. So we see quite a big jump there, where of course there's nothing like that in the globe. But what would be the results of something like that? An 833 mile inner sun and a 1,400 mile per hour outer sun. Well, what you would get is, because the sun is continuing to move faster as we approach December, everybody on Earth is experiencing the same thing right now, which is your sun sets and the amount of time until there's no light is diminishing. And that is, of course, flies right in the face of heliocentricity or the globe Earth, because on the globe Earth, you should have the north and south having opposite thing happens at opposite times, or opposite things happening at the same time. And that's not what it seems to be happening. It seems like everybody on Earth is experiencing exactly what you would expect if everyone on Earth was experiencing the sun moving faster right now. And every day that goes by, it continues to move faster. And till we get to December, and then December 21st, we'll all start marching back the other way together as we approach June. And anybody in the north, your own experience tells you this, but we do want more people testing it. And even if you just came back and said, hey, I tested it, 3 weeks in a row, and each week my sunset or my sun twilight time, if you will, is decreasing. And that's all we need to know. And we're just getting it so that for sure we know it's happening in the south, for sure we know it's happening in the north. I'm actually filming tonight, and then I'll do it in a week or two just to make sure for me that it's going down. But experience tells us this, because if you're in the north, let's say you're in the United States, you probably have sunset in the summer, say around June 21st, around 8:30 or so, and it's not dark outside until 10. That's what we're used to seeing in the height of our summer, which means you have about an hour and a half of twilight time. Come December 21st here in the United States, I have sunset around 5:30 and it's dark at 6. So I got 30 minutes of after sun twilight time. So again, when I'm getting 30 minutes, the south should be getting their hour and a half. And when they're getting their 30 minutes, I should be getting my hour and a half. But that's not the way that it works that we're finding out. We're finding out everybody on Earth is experiencing the same thing, which is right now, your amount of time after sunset is decreasing every day. And that's because the sun is going faster. And as it moves faster, of course, when it sets, it's already speeding off. So you're going to have less time after the sun sets until you see no more light. So if that's not clear, yes, I've got to word it a little bit better, get it a little bit more compact, but that's enough for you to understand what's going on and be able to go out and test it yourself. This is not a difficult one that has multiple people and you got to do this experiment. No, it's very simple. You just take your camera, could be your iPhone, could be P900, P1000. I've got my infrared, so I'm going to do it with an infrared tonight. And what you want to do is you just want to film the sunset. And because your battery probably only has about an hour and a half on it, make sure you start filming when the sun is at the horizon. So this is much different than a normal sunset where somebody starts filming 45 minutes before and then shuts the camera off when the sun sets. You're going to be filming from the time the sun touches the horizon or seems to touch it, and then you're going to film it until you can't see any more light. And so your iPhone will work, any phone will work or any camera will work as long as you continue to use the same device from the same location. Nothing really changes. I would ignore days that are heavily cloudy, even though, it does make a difference, but sometimes not much. Because if you've ever looked out at a sunset, you can actually see when you don't see any more light from the sun. There's always that little remnant, and then all of a sudden it's just dark. And that's the point of time that we would stop our clock, and you would be able to determine for yourself, oh, that's true. For me, in the north, as I expect, since we're approaching winter, my time after sunset is getting less and less and less. And then we've got people down in the south doing it, and they're showing right now that they're getting less and less and less as well. So the only mechanism that I think the globe will try and employ is they'll say, oh, well, we're moving around the sun, and because we are in December, we move faster, which again, they love to say it's a constant speed, but then here now it's an ellipse and we move faster, sweeping equal distance in equal time requires you to move faster, of course. And they'll say, oh, because we're closer to the sun, we're moving faster. And so therefore they have to input their lie, which is going to be, therefore people are seeing the sun set. But why did they try and hide it? And let me show you what I mean by try and hide it real quick, because this is probably one of the bigger evidences that I know that we're onto something here. Because if you go to time and date, and I'll bring it up on the screen 1 second. Jeez, I can hear everything in my headphones. This is going to drive me nuts. I can hear things that I would never be able to hear with my own ears. I'm just listening into neighbors talk, and no, that's not true, but close. All right, time and date. Let me bring this over here. And we are going to here. Okay. So at time and date, again, if you put in a location. Let's say we're going to go Los Angeles. We want to see what the twilight time is. Okay. So we're going to go here, USA, Los Angeles. Oops. Hold on one second. This is a little large. Browser. Let's get this down so you can see it. There's better. Okay, there you go. All right, so you'll see that if we go here, and they've got all these crazy, oops. Where's sunset? Here we go. So we're going to do sunrise. Okay, so this is giving you your hours of light in the day for Los Angeles. You'll see it gives you your nighttime. And then they have these weird terms like astronomical twilight, nautical twilight, civil twilight, and of course we know what daylight is. So you would think twilight means how much light is there after the sun sets. It kind of goes without saying, right? But if you scroll down and you figure out what they actually mean, here we go. What is twilight, dawn, and dusk? We learn that it's complete and total, and this is why it ties in well with today's topic, which is math reality. Of course not. And this is one example of that. The way that you would hide the effects of what I just told you, as far as us all experiencing the same thing, which would be something that you would expect on a flat earth but not on a globe earth, is you would hide it by mathematics. So what they're saying is that what they determine to be twilight is simply how many degrees is the sun below the horizon. Well, remember that the sun always moves 15 degrees an hour. It doesn't matter if it's moving 400 miles per hour above our heads or if it's moving 1600 miles per hour above our heads. The sun moves 15 degrees an hour. So by them limiting the idea of twilight, not to anything real, not to your experience, not to how much light is there, am I able to see, can I read a book by this certain amount of light? No, they simply base it mathematically, saying that when the sun is 6 degrees before the horizon, they call it civil twilight, 12 degrees nautical twilight, 18 degrees astronomical twilight. Well, what this does is hides what I just told you. It hides the fact that in the south, they're experiencing the same thing as us, because if you looked at the numbers purely, or the times, well, of course this matches the north, because the sun goes 15 degrees an hour. So whether you're in the north or the south, then your times would be switched but opposite, or would be at the same period of time of the year, they'd be opposite, meaning that when it's 6 degrees below, then 12, then 18. So hopefully that makes sense, that what they've done is, this has nothing to do with how much light you see. This is simply mathematics. Meaning that if 12 degrees below is at a certain time, well, 12 degrees below, you would know that at 15 degrees below, it's been an hour, right? So you'd be able to figure out the times, and the times, of course, are going to match the north and the south. Even though we are describing a situation where right now things are happening in the north and happening in the south that are the same, you wouldn't know that because it's hidden by the terms of astronomical, civil, and nautical twilight. And this tells you right here, civil dusk is the moment where the sun is 6 degrees below the horizon in the evening. Civil twilight is the brightest form of twilight. And it starts talking about, well, there's enough natural sunlight during this period that artificial light may not be required to carry out outdoor activities. But again, they're not basing this on actual light. They're basing it off of it being 6 degrees below the horizon. Only the brightest celestial objects can be observed by the naked eye during this time. Several countries use the definition of civil twilight to make laws related to aviation, hunting, and the usage of headlights and street lamps. That's another thing that you could prove this by, is we could do it with a photocell. Here's some claims I'll make. I bet you that if you timed the time that your street lights come on, how long that is after the sunset, you will notice that as we approach December, that number is decreasing. Meaning that the amount of time until the lights come on is going to be faster because the sun is moving faster. And therefore it's getting out of your area quicker, meaning that your street lights are going to come on every day earlier and earlier and earlier. That's not really indicative of anything because, again, the sun is setting earlier, so you should expect that. But it's getting earlier if you were to time clock it from sunset to when the light comes on. Now, if that's happening in the north, the south should be having the opposite. They should be starting their time clock when the sun hits the horizon, and then when their lights come on, they should end this time clock, and it should be increasing, but it's decreasing for everybody. So it's one of those things that we should have been seeing before, because I've always known that the evidence of this would come from this kind of anomaly of the north and south, right? There's a lot of things that the globe earth and the flat earth have in common. Dave Weiss talks about putting things in baskets. And there's nothing that really fits in the globe basket that doesn't fit in the flat Earth basket. But there are some things, for example, this, that seem to fit perfectly with the flat Earth model, but fail miserably at the globe Earth model. There's really no way, to me, that you could have everybody on a globe Earth experiencing the same thing like that when everything else is opposite, right? And again, they hide it by using these mathematical terms. Basically, again, astronomical twilight when the sun is 12 degrees and 18 degrees below. So if you were to take, let's just do an example here to show you what I mean by them hiding it. Let's take two places that are, go to Google Earth here. We're going to take two places at the same latitude, and we're going to a north-south and see if they're hiding what we say through the ideas of astronomical twilight. 1 second, it's Google Earth. Here we go. Okay, so let's take, let's go south first, since I know that less. It always baffles me that I'm closer to the North Pole than Australia to the South Pole. It's amazing to me. All right, so let's go to about, let's see, what do we have here? That's 27, 32. We'll do 27 right here. So here's your South 27. And we're going to go right to the coast here on the 27. And let's look at a place there that is going to be 27. Or we can find a place that we know, like what's this? No, where's Perth? There's Perth. All right, so let's go to Perth. Perth is on the, hello? What is that number? Perth, 31? About 31. Okay, so we're going 31 degrees, and we're using Perth as our south example. Okay, let's go to north and find something at 31 degrees. Over here, okay, let's find 31 degrees up here. Oops. So 31 degrees is going to be where? Here. Hello? Okay, here's 31. Does it go anywhere through Texas? Hopefully good. Okay, so we'll find a place in Texas along this 31. And we use that to see if there's any cities that we are familiar with. Well, Jacksonville, Florida, that's a little bit south. 31 still there. Do we know any of these big cities here? Jacksonville Beach, Palm Coast is at 29 up here a little more. All right, we'll just take 31. I don't see anything that really sticks out. Brunswick, Florida, is that even a place? All right, whatever. So we'll take Brunswick, Florida, which is on the 31. Brunswick, Florida. Okay, so now what we're going to do is we're going to see on time and date what we get for. Okay, so we're going to do back to here. And we're just going to check the astro. But here's what's going to happen. We're going to see that they, Brunswick, Florida. New Brunswick, what? Of course I find a place that's not on here. Brunswick, Florida. Is that how you spell it? Okay, 1 second. Couldn't make it easy on me. Doesn't that say Brunswick? Brunswick. Okay. Let me see if we can find something else that actually makes sense. 31 is going through here. There's no big cities on 31. Come on. Simsport, Texas. Let's try that one. Come on. Give me that. Simsport, Texas. Okay, what the hell's going on? Am I tripping out here? Why am I not getting any places on 31 degrees? 31 over here. 31 over here. Is there some big city? So does time and date only show big cities? I thought you'd be able to search any city there. Van Horn, Texas. I've never even heard of these places. Killeen, Texas. Waco. Waco's got to be on there. It's close enough. We don't need it to be exact. Let's try Waco. W-A-C-O. There we go. All right. So here's Waco, Texas, about 31 degrees or thereabouts. And we're going to be looking at their. So let's go to December 21st. If we can. Let me see where we put in the date here. Sunrise, sunset. where do we change the date on here? Oh, we gotta go here. So October, December, where's December, November? It's right here. Okay, we're gonna go December, go. And we get December 21st. Okay, so we're looking December 21st here for Waco. Just writing this stuff down so I don't lose it. December 21st, Waco. Okay, so we've got sunrise at 7:23 a.m., sunset 5:29. So 5:29 sunset. And then we've got, 5:29 sunset. This is daylight difference. So they've got basically 10 hours. I'm just going to write this down to see if it's the same as there. 10 hours and 5 minutes of daylight. Okay. So astronomical twilight starts at 5:56, ends at 6:56. That's not what we're looking for. We're looking for start at 6:26, end at 6:26 p.m. Okay, nautical twilight, civil twilight, this one. Okay, so we'll see here 5:56, right? So if it 5:29 to 5:56 is 25 minutes. Yep. So that means in Waco, Texas, you have 25 minutes of supposed twilight. But again, this is going to be done mathematically. Don't expect it to be any different at the opposite time down south. Okay, so we got pretty much all we need from here. Let's now go to Perth. Okay, so we're going to go to Perth. Was our other place? Yes, 31 degrees. So we're going to Perth. Hello. Yes, so we're going to Perth here. All right, and we're going to go down here to find, first let's go to December 21st. Then we'll go to June 21st after, but let's go to December 21st. Oops, December. Yes, go. And we're going to the 21st. All right, so we've got a 5:06 sunrise, 7:21 sunset. Wait, what? On December 21st in Perth? That seems weird. Okay. I guess I thought it would be later. So daylight, 14 hours, 14 minutes. Okay. For Perth. 14:14. And then we've got astronomical twilight here. And we've got civil twilight ending at 7:49. Okay, so if you look here, we've got a difference of 28 minutes. Is that correct? I believe 28 minutes. And for Waco, we had 25 minutes. Okay, so I guess they're not really hiding something here because that seems to be incredibly short for their summer. But let's see what happens when we switch to the winter, because that doesn't make a lot of sense to me. If in Perth in the summer, sunset 7:21, and the end of is just 28 minutes later. Okay, let's go see June 21st. Okay, here we go, June 21st, and we get sunset at 5:19. We get a daylight time of 10:03. And in Waco, we had 10:05. So we've got pretty much the opposite at the opposite end of the year as far as daylight hours. And we get twilight ending at 6:17, which is, 5:47. Correct? Yeah. So 5:47 is 28 minutes. Okay. So here's the problem. Is it's 28 minutes because that's the calculation of the degrees, right? Like if it's 15 degrees an hour, then half of that is 7.5 degrees per 30 minutes. And so at 6 degrees, it's probably around 27, 28 minutes. So it's being done mathematically, not by actual time after sunset. I did not know it gets, that it's so weird that they say it's opposite, but we just saw in LA it gets dark at 9:30. I gotta go back and see something real quick. Or not in LA, Waco. Or was I tripping out? because that is clearly not opposite. Let me see. We go back to Waco. Let's type in Waco again. And then I'll ask Alan, am I doing anything wrong? Or I am looking at 31 degrees north and south. I am looking at opposite times. I would think that their sunset times would be the same, but I'm not seeing that. So let me see again. Waco. Oh, wait. Waco. Oh, no, we want to go December. June 2023. Go. Okay, so this is Waco now in June. And the sunset is way later. Sunset 8:36. So already, and again, this is something I would expect with a flat Earth. But I expect to see the same sunset times in Waco and in Perth, and we're noticing different times by an hour, or at least. 14:12 as far as daylight hours. 14:11 was Perth. We've got sunsets 8:36 and 9:04 is the end of civil twilight. So again, this is, it is being hidden in the way that we're just going to keep getting the same numbers. So every time we look, we notice that it's about 28 minutes after sunset, right? 36 would be 24 to get to the top of the hour. 24 and 4 is 8. So 28. So again, we're at 20, we keep finding 28 minutes, but that's because that's mathematically figured out, right? If this is 6 degrees below the horizon, and you'll kind of notice that it's not going to change much per your, see here, we go from 8:32 to 8:37, so a 7-minute change. And here we go from 9 to 9:05. I thought it would be 7 minutes, but it's close enough. That and again, they're basing it off of math. So am I missing something here, Alan? Are you there?
No, yeah, I'm here. So
Okay.
you're saying you keep finding a 28-minute discrepancy?
No, it's not a discrepancy. I'm finding that because they've made it mathematical, then
Right.
you know, I keep finding 28 minutes of twilight after the sun sets, no matter where we go, though, because
Didn't you find some significance with 28 minutes in the moon or something, and with Elias?
oh no, that was with
Or was that something else?
that was the 50-minute, or I'm sorry, the 24-hour 50-minute. Yeah, Elias kept saying that he kept finding something that happened with his pendulum was happening on 24-minute and 50-second cycles, and he kept saying, I don't know, there's no significance to 24 hours and 50 minutes. But there is, because that's the time that the moon takes to orbit. And then I took
dude, no way. Okay.
yeah, but if
Okay,
you
I
take,
didn't understand. Okay.
but watch this math. So this is crazy. So if we know that the moon takes 24 hours and 50 minutes, so that's 24, so 24 times 60 is 1440, right? And then we have the extra 50 minutes, so it's 1490 minutes, okay, is a moon day. And we know that right now we have to do, for leap year, we have 365 days in a year, but it's actually 365.25 because every 4 years we have to take a leap year, right? So it's not exact in any way. The year's kind of screwed up. But if we take 1490, which is the moon day, and then we figure out how many days are there in a year. Well, if there's 365.25, according to them, and we multiply that by, so that's 365 days, we multiply that by 24 hours equals, and then multiply that by 60 minutes, we get 525,960. So it means in a real year, technically speaking, it would be 525,960 minutes. So if I divide that by the 1490, it would be really strange if it came out to something pretty perfect, right? Well, it comes out to 352.999288859. So if you count the moon days, the year is perfect at 352.999 moon days. And I bet you the part that I'm missing on the 0.999 to get it to 353 is because it's not 365.25, it's actually and change. It's like 365.25 because you don't do it every 4 years. You do it every 4 years except years that end in 00 and never after 400 years or something. So it's kind of funny that the moon actually describes a better. Now, again, I'm fully aware that human beings could not calculate days by the moon. That would be very difficult to do because it would constantly change, right? Like it wouldn't stay consistent. The moon rises every day of every hour of every day, meaning that it's always changing. So it wouldn't be as set as like the sun that I know is going to rise between 5 a.m. and 7 a.m. No, the moon could rise at any time of day. So if we did days by that, it would be as screwy as all get out. But it's still pretty crazy that Elias was finding something happening to his apparatus at 24-hour, 50-minute intervals. Pretty crazy. So anyway, back to this. So there's really, I mean, this is why you're not going to really find anything in time and date, because this isn't telling you anything reality. Now, it is telling you reality, sunrise, sunset. But then when it talks about twilight, this has zero to do with anything to do with how much light you see. Is it simply when the sun is 16 degrees or 6 degrees or 12 degrees or 18 degrees below the horizon, which is going to be basically a clock. It's math. It's not observations. You know, you could see light for longer. You could see light for shorter. Who knows? Well, clearly we're going to see, let me go back. Are we still Waco? We're still at Waco, and we're in June 21st. Okay. So 8:36 is their sunset. And in my guess, you probably don't get dark until 10. Okay. As far as it being fully dark. Let me see what it says. So astronomical twilight. I'm going to kind of check this and see what this. So this is supposedly 18 degrees below. I believe if we, I want to check that real quick. Astronomical is what? Astronomical is 18 degrees below. Okay. Go back here. So I just want to see the times difference between those two. So we've got the 21st, 8:36 to the first number here, 10:16. 8:36. 10:16, so that's going to be an hour and 40 minutes. Okay, which sounds about right to me, about as far as when we can't see any light anymore, is about that time in my summer. So we got an hour, 40 minutes till we get to that 18 degree mark. So now we're going to go to their summer, Perth summer, which would be December, to see if we see basically the same thing. Okay, so we're going to December and go. Okay, so we're going to the 21st, and we've got sunset 7:21, and we've got astronomical twilight 9:01. So again, we've got exactly an hour 40. So what somebody looking into this cursorily would do is say that, no, this is matching up exactly to what we expect on a globe, because 6 months later, we're getting an hour 40 minutes after sunset. They're getting an hour 40 minutes after sunset. Okay. But where they're hiding this is they're basing this number off of the 18 degrees below the horizon, which of course it's going to match. That's how they hide it. It's 18 degrees below the horizon. Since it goes 15 degrees an hour, is the same for the north 6 months later than the south, or 6 months earlier, vice versa. So this is essentially the way that they hide it. But I've already got a problem with the fact of, how do they explain a sunset an hour early? It might be something to do with daylight savings, or I'm not sure why that would work. Why would it be at 7:21 in Perth in December? Just seems crazy. But again, it makes sense on a flat Earth to me. They are getting the longer days, 14 hours, but the sun's moving faster, so you get the final sunset. We had 10:00 something, and they're at 9. So why would it get astronomical twilight end so early compared to the north? It should be the same times, but not. And then let's just check real quick on the June. Oops, go. June 21st for Perth. We're in Perth still. We've got a sunset at 5:19 and a end of twilight at 6:47, which is an hour 28. About an hour 28. Okay, hour 28 until the end. And let's go one more time back to Waco and check on June. Oops, nope, I want to go to December. Let's see what they've got on the 21st. 5:30, 5:29 there, 5:30 to 6:56, which is an hour 27. Yeah. So hopefully what I'm showing you there is that they've hidden this, because what we're talking about is an actual observation, that you're actually seeing the light disappear faster. You're actually seeing the light hang around more. But what they've done by wrapping this up in math is basically made it so that you can't see it by going to time and date. And I don't know anybody who's out verifying the times of astronomical or nautical or civil twilight, because who are you going to argue with, and what are you going to say? Hey, this says astronomical twilight ends at 6:56, but I still see some light at 7:22. I mean, nobody cares, right? So anyway, let's move on with Alan. Alan's going to be doing a little presentation on math being not reality, or how they turned math into reality. And also just a reminder, if you want to help out with this experiment, it's very easy. You can feel like you contributed. You can see it for yourself. Just need a camera and a couple days. If you could do it 2 days a week, that'd be great. But if you only can do it 1 day a week for the next, say, 3 weeks, and all you're verifying is, yes, Jeran, the sunlight time is going down. You know, that you don't even need to really show the video, but we're just trying to make sure, get all our ducks in a row before we go public with this or big with this, because we probably should mail universities and things like that for something that's clearly been hidden. That's always something you got to look at, is if they were not afraid of things, then those things would be out in the open. The fact that everybody on Earth is experiencing the sunlight time decreasing at the same time, and then everybody's experiencing it increasing at the same time, they hide that for sure. There's no reason why none of us have ever heard of that. If we're always told it's the opposite, to just find out now, wait a second, so everybody on Earth, the sunlight time is going down. We're just told, no, when it's our summer, they're getting longer days, and then we get shorter days, and then when we get longer days, they get shorter days. True, but that would be the case on a flat Earth as well. And another added effect would be the sun is moving faster, so clearly there would be some effects of a faster moving sun compared to a slower moving sun. What kind of effects would those be, Jeran? Oh, well, if the sun is setting faster, moving faster, then after it sets, you're going to lose light faster. And that's what we're actually seeing. So reach out on Telegram, t.me/Jeranism, and just say, hey, I want to be in the sun watching group, and I'll give you that link. And there's already 10 people or so in there talking every day about their observations. So you can join that club if you want. All right, Alan, it is all you, my friend.
All right.
You going to share your screen?
Yeah. I'm gonna share screen and we'll get into it here. Okay. All right. Can you hear me?
You're great.
Okay, cool. All right.
And if I have any questions, do you mind if I stop you during it, or you want to wait till the end?
No, absolutely. So if you have any questions or you read a good question in the chat, feel free to interject. How are we doing on time, by the way? Because this is kind of a
you have
long
good
presentation, but I can.
What were we going to try and do, like an hour?
Yeah, easy.
Okay.
Yeah,
let's try it an hour or less, and I'll probably stop you a few times. So.
Yeah. Okay. Cool. All right. So we'll get into it here. So this is to cover the basics on how math became reality, how general and special relativity superseded the ether framework and became the mainstream interpretation of physics, and why everything was redefined. So let's see, to get a better understanding. Oops. Hit the wrong button. All right. Why is it not letting me? Not letting me change scenes. Hold on one second.
No problem. Eric, I don't know what happened. I see you in the chat. I just looked over there. I looked at your channel. You're not blocked or anything. I just got blocked. What does that mean?
You are currently sharing. What the heck? All right, one second. Stop share. Close PowerPoint. Slideshow. Their screen. All right, is that sharing?
Yes, we see it.
All right, cool. All right, now we're good. Sorry about that.
No problem.
Okay, so this is how they brought math into reality, and they tricked everyone into believing that a coordinate system bending and warping simultaneously is responsible for the behavior of light. So abstract. So to get into special relativity real quick, this is just to explain what that theory is and what its purpose was. So it's basically just the relationship of velocity, movement, right? And it's saying that when you're experiencing movement, you can't measure it, and then it gets into reference frame transformations, and it was basically the jumping off point for explaining things with abstract mathematics and using coordinate system transformations to describe a bending and warping of space and time. So what they did with special relativity is they added a fourth axis to the coordinate system, which is time, and they added that perpendicular to the direction of motion, right? So the x-axis. So, so whenever you see the time coordinate, it's always perpendicular to the direction of motion, and there's a hyperbolic contraction relationship there, where time and space contract proportionally to meet the speed of light, and that's their jumping off point for all of that, right? So and then in the general theory, that's where they use mathematics, or use the abstract mathematics to describe a gravitational field, which is a field is a mathematical concept that uses vectors to indicate a direction or intensity distribution as a force to describe a phenomenon. So when they're talking about abstract, or when they're talking about like a light in the sky and its behavior, and so they came up with this coordinate system to describe, it bending and warping, and this is how they do that. So they say that the gravitational field is its force is impacting space-time, and space-time, which is the coordinate system, is bending proportionally, and that's facilitating the movement in space and all that. So that's how they did that. And then through a couple of principles, namely the equivalence principle, the general theory is linked to the special theory mathematically, where a gravitational field, right, the abstract mathematical construct of a of a gravitational field is supposedly equivalent to experiencing acceleration. So that's what they did there. And so the overall goal of this presentation is to leave you with a better understanding of special and general relativity, even if you don't agree with my final summary on it at the end. All right, so to get everyone to believe in the general theory, right? So the special theory at this point was already a little rocky with interferometry. As the progression of interferometry went on, the varying speed of light was being shown, and the special theory was unable to explain it. So they had to quickly rush in the general theory. So they had two calculative predictions for the general theory, and one was the perihelion precession of Mercury, which is just the mathematical calculation of how much they're saying the coordinate system is bending and warping and all that. So not necessarily anything meaningful in that, right? But then there was a deflection of light prediction. So that gives a little more credence to the coordinate system situation, and then also to establish a cause and effect relationship with that deflection of the light. There was a gravitational redshift prediction. So what that means is they were going to predict how much the light spectrum was going to change as it interacts with the curvature of space-time due to that gravitational field bending and warping it, right? So these three things tied together were supposed to provide a meaningful way to bring in like, hey, this is what's physically happening. Time and space are joined. They're gravitational fields cause a bending and warping of it. And this is what happens to light when it interacts with it, as predicted by the theories, right? So this was supposed to establish that cause and effect relationship with it, right? So we're going to go over a little bit of terminology here to get the baseline, and then we'll just breeze through the historicity of it, of these experiments, right? So an arc second, so these, when they're measuring stuff in the sky and all that, they're using arc seconds. So if you look at a protractor right here and you look at the difference between 1 and 2 degrees, you can break that into 60 arc minutes, and then you can break that 60 arc minute into 1 arc second per minute. And so that further divides down. So in 1 degree, you can have 360th of a degree. Like you can break it down that far. And then when they get into milliarcs and microarcs, that's 1,3,600,000 of a degree, and then 3,600,000 of a degree. So when they get to that stuff, that's usually when they're talking about stuff that they're using like quote unquote space satellites for, where there's no atmosphere, where they can get these really precise readings and high magnification and all that. So, but for the terrestrial stuff, they're usually in the arc second range and arc minutes and all that. Right? So metric tensor. So these are just mathematical descriptions of coordinate systems and matrices to describe the coordinate systems. So we're not gonna waste too much time on this. So just to show the practical usefulness of how tensor calculus could be used and stuff in a meaningful way, right? So say you have an I-beam here and you want to describe any particular point in this I-beam and any stress that's related, that it might be experiencing due to whatever factors might be going on in the coordinate system, right? So you could describe all of that, and you could add like the tensile strength and stuff of the material and all that, and have meaningful numbers and calculations based on like real forces and all that. And you could figure out the relationship between, like, for example, let's say this point in the I-beam is going to be experiencing this much, stress, in proportional to this side of the I-beam because it has more, structural support or something like that, right? So you could derive all of that with these coordinate systems and tensor calculus and these metric tensors and stuff like that. So it does have practical use, right? So it's a real thing, right? So that was to showcase that. So let's see. So there's different types of metrics that they use in space and general relativity math. So they got your Schwarzschild metric, your Kerr metric, your FWR metric, and you got your curvature tensors. All of these serve different functions. Usually it's just describing how space-time is curving and what's in space-time and that sort of relationship. And then you got your, let's see, curvature tensors, which describe the gravitational fields and your conservation laws. All right. So in combination with that, they're just basically building a combination. They're basically, if you could think of it like they're describing an abstract coordinate system to define a giant I-beam in the sky in a gravitational stress relationship between 2 points, right? So that would be a kind of way that you could look at it. So when you get into spectroheliographs and spectral shifts and that kind of stuff, so what you're looking at is just look at a telescope, and then you're looking at a star. The light's coming in and hits a prism, and the beam gets split up into its respective colors, and that gets hit on a photographic plate. And you can, what they're looking for when they talk about redshift, so they're looking for slightly more red. When they talk about blue shift, they're looking for slightly more blue, and they correspond that to Doppler shift, where red would be moving away from you and blue would be moving towards you. So I think Robertson Jenis said it really well. Their light's hitting a prism. They're looking at a rainbow spectrum, and they're looking for slightly more reds than blues and stuff like that, right? So really easy way to conceptualize what they're doing when they're talking about these types of observations. They're just looking at light, splitting it through a prism, and comparing the color, right? Then a quick note on Doppler shift here. So we got a car here moving towards an observer. Now, the medium in which the sound wave is propagating through is air and water vapor. And as the car is moving towards the observer, these waves are going to get compressed. So it's going to produce a higher pitch when it's moving towards the observer. And that compression is going to be facilitated by the medium and the motion of the observer. Of the source in this case. And then as the car moves away from them, the medium and the motion is also going to facilitate the expansion of those waves, and you're going to hear that low pitch. So what's changing that high to low, or what's facilitating that wave compression is that medium in which the waves are propagating in, right? So that's a way to think about it. So how they attribute that same high-low pitch situation with starlight is a redshift, blue shift situation. Let's see, I'll just go ahead and skip that. But that's basically what they're doing there. So let's see, standard observational conditions when using a telescope. So this is just to give an idea of your basic observational conditions. So this is a quote from McRoberts in 1995 from Sky and Telescope magazine. Viewed at a high power from the bottom of our ocean of air, a star is a living thing. It jumps, quivers, and ripples tirelessly, or swells into a ball of steady fuzz. Rare is the night at most sites when any telescope, no matter how large its aperture or perfect its optics, can resolve details finer than 1 arc second. More typically, or at ordinary locations, is the 2 or 3 arc-second seeing or worse. So that's just to give you the average visibility that you can see with current equipment. Well, even like they were saying with the best stuff, it's just really going to depend on the conditions and what you're trying to look at, right? So how much atmosphere you're trying to look at or look through. Okay, so now that we've got our prerequisite information of the terminology that's used, we'll get into the proofs that are put forward. So for the perihelion precession, this is just a calculative prediction. It's not very meaningful, but the big huff and buff or whatever is that Newton had a prediction that that could only predict 55, 57 arcseconds per century of perihelion precession, and relativity theory could predict the full 5600 perihelion precession over the course of a century. So keep in mind, these observations weren't even made over a full century. It's just a mathematical extrapolation of how they think Mercury is going to continue to move based on Urbain-Le observations over, I think it was about 30 or 40 years. So they had this whole thing where they were trying to come up with a way to do it. So under Newton's model, he imagined light was a little corpuscle, which was like just a little tiny particle, and he thought that gravity would act on it similarly to a mass attracting mass situation, and that it would pull light toward it. So he predicted that it would bend by a certain amount, but less than half as much as Einstein predicted. And these are postdictions, not predictions, right? So keep that in mind. So anyway, Einstein's theory, quote unquote, predicts the full 5600 deflection, meaning that light deflects more, and this is based on a different mechanism than Newton's in this. And Einstein's mechanism is that space-time will curve due to the gravitational field of the sun. Okay, so to conceptualize that, here's a nice MS Paint drawing. So imagine here's the sun, here's the equator of the sun in black, here's your boy Mercury orbiting the sun every year, and then they're saying there's a slight displacement by 1 pixel over the course of a century, and Newton could only explain half of a pixel shift, and Einstein could explain the full pixel shift. So that's hopefully that breaks down the big debacle that they were having that needed to be settled, right? And keep in mind, 18 years prior to Einstein coming up with the full solution to this, a physicist and teacher named Paul Gerber came up with this solution 17 years earlier, using the same exact, his exact equation somehow ended up being the same exact equation that Einstein used, only Einstein changed 2 symbols in the equation and changed the meaning of one, and that's it. So the reason that Paul Gerber doesn't get credit for proposing a solution to the perihelion precession under Newtonian dynamics is that he used an ether theory, and the way that he related the propagation of the gravitational wave is through that medium. And they didn't, then they were past the ether at this point, right? So they didn't want to use that. So Einstein rolled through and just swooped up his whole framework and just said that, you don't actually need to add a limit to that. We can just use the time it takes, the total time it takes for the orbit or whatever to complete 1 year, and we can distort that coordinates system to give the enough warping for the 5600 arcsecond over the course of a century, right? So that's how they did that. So keep in mind, these equations are identical, right? And Einstein has been flat out accused of plagiarizing off of Gerber, and Einstein's direct quote, and you could read this off Wikipedia, how he defends himself. Einstein says, "How could I have plagiarized Gerber's work if I've never read Gerber's work?" Oh, cool, man. So Einstein also plagiarized Lorentz's work. Real quick, we'll just dive into that. Let's see, a couple years after Michelson-Morley, so this will be like 1898. Lorentz published something on Michelson-Morley in his ether explanation with ether contraction. And Einstein wrote a letter to his wife saying that he was really interested in Lorentz's work and also Lorentz's work on the moving bodies of electrodynamics and his explanation into that. And he was going to be looking into them. And then several years later, 1905 rolls around. Suddenly, Einstein's special theory comes around, and it's based off of Lorentz transformations, adheres to Lorentz symmetry, which is otherwise known as Lorentz covariance. So, like, basically the exact framework that another guy named Lorentz set up, who isn't named Einstein. Like, it's not called Einstein transformations or covariance, right? So, and he didn't even credit him in his paper. So, anyway, he's got a history of just, co-opting someone's entire framework and just, saying, hey, this is something I thought of that would be really cool while I was working at my patent clerk job at the office. So let's see here. Let's see. So we went over that. So Paul Gerber. So to recap on that, Paul Gerber had the mathematical explanation, the physical mechanism, everything, but they were past the ether at that point, so nobody cared. And then Einstein swooped in and just took it all, right? So let's see. Conclusion. So these are, let's see. Perihelion conclusion. So there's a lot of possible explanations for what could cause, that quote unquote disturbance in the sky. It doesn't have to be related to a gravitational field. It may or may not even exist at all at this point. But let's see. There's theories. So yeah, the way they try to explain it through relativity, though, is they give this calculation where they say Mercury doesn't weigh anything, the sun isn't moving, it's not rotating, it doesn't have any energy, no electricity, nothing, no charge. And they have an exact amount that they need space-time to bend and curve to predict this amount. So they've just come up with a way to impose an ideal situation to reify their coordinate system. But again, people, weren't ready to fully accept this as proof, right? Because this is just a calculative way to predict things, right? So then we get into the deflection of light rays. So we've all heard of the Eddington observation and all that, right? So this is how much they allegedly predicted how much starlight would bend, based on their assumptions about how gravity works, being the gravitational field, being the bending and warping of space-time and the distortion of it, or the mass attracting mass Newtonian physics description of it, right? So to settle the matter, Arthur Eddington came in May 1929. British astronomer Arthur Eddington led an expedition on the island of Principe off the west coast of Africa during the total solar eclipse. The purpose of the expedition was to determine the accuracy of the two theories regarding the displacement of starlight. And this was going to help facilitate more of a physical mechanism to the coordinate system, because remember, everything back prior to this, or prior to relativity, was ether physics, and everything was, had to have a mechanical cause and effect relationship. There had to be some sort of motion. There had to be pressure mediation through it, right? So like this was like a well understood mechanism for how things worked and how they were explaining it. So to replace that and to say that no, this abstract math concept, like they really needed some physical proofs of this. So this was where we're going to get into how they were going to start facilitating the magic trick, so to speak. So let's see here. Theories, no influence of gravity and the effects of coordinates. Okay, so when we get into the observations that Eddington may or may not have made, he took 16 photographic plates, and his boy Cromlin took 16 photographic plates. Cromlin went to somewhere in Brazil, somewhere in the west coast of Brazil, and he took his observations. Now, he said that due to a temperature differential, that his apparatus, contracted during the eclipse, and and so his measurements aren't accurate. They can't be used to determine anything. So only Eddington's observations could be used. And then from Eddington's 16 photographic plates, only 2 of those were usable because of different weather conditions and whatnot. Apparently, they had a bunch of conditions and stuff that they didn't think of. They just thought they just thought they were going to roll up, take some quick shots, and be done with it. But it was actually rather difficult. So overall, they ended up with only ended up with 2 photographic plates that gave Einsteinian predictions, and this was Eddington writing to what's his name, Frank Dyson Watson, on his way back from after the observation, stating that the 16 photographic plates were poor, and only 2 of them really looked good, and they would have to do later analysis and stuff like that when they get back, right? So let's see here. So to get into so after they get back and they do their analysis of everything, your boy Frank Dyson Watson contributes to a statistical analysis of the transformation of the photographic plates, because apparently the reference plates that they took for the before and afters, the befores couldn't be used, so they had to use pictures that were reference plates that were taken a year prior, that were used that had different materials and stuff. So they had to come up with a way to compensate and all that. So this guy stepped in mathematically to make these corrections. So these are really fine, precise measurements, down to the, what is it, like 0.00 millimeters type stuff, really, really small, back in this time that they were doing this with. So Dyson brought everything in alignment with relativistic predictions. And then moving forward, on November 6, 1919, there was a meeting of the Royal Society and the Royal Astronomical Society, where the bigwigs of the time got together and were going to announce the successful confirmation of general relativity and the predictions of Einstein matching the starlight displacement. And so I'll read a couple excerpts from here. But it's basically just a back and forth, and then we'll get into the gravy towards the end of the conversation, what they said here. So this is Sir Joseph Thomson. This is the president of the Royal Society. He makes his announcement with a decisive conclusion and announcement that relativity theory has been predicted based off of these 2 photographic plates, and everything's on the up and up, and it's really exciting moving forward, and he's super pumped. And keep in mind, this is the president announcing this. This isn't... this is announcing it for everyone, right? This is the first public announcement of this, so to speak. So he isn't like, hey, we're going to look at this, examine it, or anything. He's like, hey, moving forward, we got this. This is dope. So we'll go over a couple quotes here, some photographs. Fowler.
Alan, what would you say to somebody who always hears back when we say relativity is not proven or whatever? They say, oh, the star that they saw behind the sun. What would be your best one kind of liner come back to that? Or would you say that it's, actually they observed it somewhere totally different, observed it on the wrong side? What's your answer to that?
The reason plasma cosmologists abandon relativity and become plasma cosmologists is because they look into the Eddington observations, which is all this hinges upon, that mechanism to facilitate that energy transfer to even cause displacement in starlight, right? So when they actually look into it, what they find is that only 2 stars showed displacement within the solar limb of the sun. So not even out here. So like going back a couple of slides where they try and talk about like stars over here and over there and all this stuff. No. They say the only stars within this region right here of the sun, this circle right here, is what was displaced. So where there's already assumed to be a magnetic field, an electric field, a plasma medium and all that stuff. So when they realized that everything hinged on that, and that there's already a medium there, that's why they became a plasma cosmologist. That's why they abandoned it, because everything hinged on the facilitation of this coordinate system, this abstract coordinate system accurately reflecting light, or reflecting reality. I'm sorry, portraying reality. Hinges on this. It hinges on this observation that didn't exist. So that didn't really happen. And when you pull up stellarium and look at that observation, there's no stars within the solar limb. That guy QNFE, I can't remember the numbers on his channel. I think it's like QNE77 or something like that, or QNFE. He has a great video on the Eddington observation. It's hilarious. He pulls it up in stellarium. There's no stars within the solar limb where they say that this even happened. And the two photographic plates that supposedly prove this are lost to history. But all the photographic plates that don't prove Einstein's theory that that Cromlin took that don't prove him right because the temperature differential, all those photographs exist, and you can see those today or whatever, but like completely meaningless. But the actual evidence supposedly can't be examined because they lost it. It got broke or whatever, garage sale, that kind of thing. So that's what I would say. That like really smart men were like, hey, this doesn't make sense. We need a medium. We need a mechanism. That's what I would say.
Okay, thank you much.
So let's see, where do we leave off here? So these men got together and all decided that relativity theory was the bee's knees and they were going to push that forward. A couple guys gave some pushback. There were some questions about the medium situation that I was bringing up here. So actually, when you read this transcript here from this meeting, there's a couple, like they're actually bringing up this exact topic where they're like, hey, I'll just get to the gravy here. So this guy who I'm dubbing Whitsitt's great grandfather, Dr. Silberstein, he steps in and brings up this point. So I'll just read out the full text because it's very important, the full context. But in spite of what the president said about the successful confirmation of relativity theory based on the starlight displacement, supposed starlight displacement, I believe this result to be essentially an isolated fact. There is a deflection of light rays, but it does not prove Einstein's theory. It cannot logically be deduced from it, a theory as a gravitational effect in absence of the spectroscopic results. And as far as we know from St. John's and Evershade's observations, the predicted shifts of the spectrum lines of the amount exceeding almost 100 times the amount of probable error of the modern spectroscope, as Professor Fowler has just told us, was not obtained. Professor Lindman's attempt to explain the obstinate nullity of the effect of the motion of the luminous gases in the line of vision is not satisfactory, for St. John was well aware of such complicating circumstances and therefore purposely observed as many as 43 lines at the sun's center and as almost as 43 lines at the sun's center and almost as many as 35 at the sun's limb. Now, we cannot assume that the gases move everywhere towards or away from us only to suit Einstein's theory, i.e. just to compensate for his theoretical shift. So this is in reference to the gravitational redshift that we haven't touched on yet. And the mainstream narratives really don't talk about the gravitational redshift aspects of this at this time because they were a complete abysmal failure for establishing a cause and effect relationship with Einstein's theory. And these two men, St. John's and Evershades, would not go along with Eddington and just saying that, it did work out, like lying basically, right? He asked them to lie and they wouldn't do it. And the spectroheliograph. So what we were talking about earlier with breaking starlight down into a rainbow and looking at the prism. So what they were looking for the gravitational redshift predictions, if there was an interaction with the photons, traveling, from starlight or whatever, in interacting with the curvature of space time and all that, there would be a frequency displacement, right? There would be a color displacement that they would be able to get out of that. So that's what these guys were looking for, and they didn't find any of it. And they don't talk about this at all because, like I said, it was a complete failure for establishing that cause and effect relationship. But this guy points it out really well here, so I'll continue reading. So as I have already pointed out on another occasion, if there is no spectral shift, Einstein's coefficient GUV, which is how he describes his tensor for space-time curvature, which is entirely responsible for the displacement, there must be unity. And if we go back to the differential equations, Einstein's field equations, we shall see at once that the other coefficient as well, or in his well-known approximate solution, becomes unity at the same time. This being, and then he gives the equation here and another equation, And this for that the world element simply reduces to, and the world element. So earlier when I was talking about space time and time being added to the axis where it's proportional to the where it's perpendicular to the direction of motion. So this is what he's talking about. They call that the world line or world element. Let's see. The world element simply reduces to zero. So he's saying that if there's no bending and warping and no curvature, you know, then your explanations don't make sense, because the equations of motion are always given by, and he gives the term for imaginary numbers for just saying, like, you know, this is an imaginary thing. We ultimately see that the spectral shift is absent in Einstein's theory. Not only does, or I'm sorry, we ultimately see that the spectral shift is absent. Einstein's theory does not only give such refinements for the planetary motions as in a secular motion of the perihelion, but not even in the ordinary Newtonian or Keplerian motion. In short, the orbits of the planets would be straight lines, and the planets would move along them uniformly in spite of the sun's presence. The theory stands or falls on the correctness of the results of Evershades and St. John. So what he's saying there is space-time, the way that they describe orbits is everything is traveling on a geodesic, everything's traveling in a straight line. But space-time, the coordinate system in which this straight line is traveling, is curved due to the displacement of a gravitational field, right? So that displacement ultimately means that straight line is actually curved, and that's the mechanism by which they're describing that's how they describe the abstract mathematics, and they say that that's happening in the sky, and they say that when they look at Mercury and they see that little tiny perihelion displacement or whatever, they say that that's due to space-time curvature. So this was all about establishing that, and like Whitsitt's great grandfather said, the theory stands or falls on the correctness of that gravitational redshift observation, because it would establish the cause and effect relationship with that displacement, right? I mean, it would be pretty undeniable if they could get that right. So, or at least it would provide a lot of positive evidence, right? So it is unscientific to assert for the moment that the deflection of relativity theory, which I admit is due to gravitation, it is in this sense that I declare a moment ago it to be an isolated fact. The discovery that was made at the eclipse expedition, beautiful as it is, does not, in this circumstance, prove Einstein's theory. We owe it to that great man over there, pointing to Newton's portrait, to proceed very carefully in modifying or retouching his laws of gravitation. This is by no means defending blind conservatism. The spectrum shift required is perhaps 100 times, but certainly not less than 40 or 50 times the error of modern measurement. The solar spectrum can even in this country be observed many times in the year, and the matter can thus be decided without having to wait years or centuries for another equally advantageous eclipse. If the shift remains unproven at the present, the whole theory collapses, and the phenomenon we just observed by the astronomers remains a fact waiting to be accounted for in a different way. All right. So in summary there, those guys, St. John's and Evershade, they found that they could use Venus transits as well to get gravitational prediction or redshift predictions as well. And they never found any redshift. They never found any predictions that corresponded with what Einstein predicted. So we already went over the significance of what they were trying to establish with their coordinate system. Let's see. So here's Eddington's rebuttal to what Dr. Silberstein just said. So one word to Dr. Silberstein: when a result has been forecasted, is obtained, we naturally ask, what part of the theory exactly does it confirm? In this case, it is Einstein's law of gravitation. It is not necessarily his theory that is confirmed, with the underlying assumption that ds is the quantity measurable by clock and scale. There is that remains the question of the intermediary quality of what ds is, which must be tested by the Fraunhofer lines. And the Fraunhofer lines, again, is in reference to the spectroheliograph readings. So that's the displacement readings. So when they look at the redshift stuff, that's what he's referencing. They called it Fraunhofer lines. And then ds would be your space-time. That's what he's talking about. So the coordinate system describes space-time and starts out with ds with the first interval. So that's what he's referencing there. So that was his big refutation there. And I didn't add this letter yet to the presentation because this is something I found out after the fact and just haven't added yet. But anyway, Eddington knew all about the validity of what's his name of Silberstein's critiques, because he wrote to a Swiss mathematician named Hermann Well about 6 months before the Eddington before his observations in May for the eclipse, and he said, "Hey man, we're having a real problem with this gravitational redshift situation. St. John's and Evershade are being reluctant in being able to find what's it called, gravitational redshift lines, giving agreement with Einstein. So we need to and I'm looking at your theory, and maybe you can help me out here, because this guy was working on a universal theory of explaining everything with a bunch of complex abstract math. So he was writing to him 6 months before all of this, so he was well aware of all this. And here he is acting like, "Hey man, like we don't need to know what the cause and effect is. Like we have the calculative numbers. So let's just keep running with it," right? So November 7th, so the next day, they successfully announced, the British media and U.S. media announced that Einstein was the man, and he was catapulted into stardom with his predictions, and his laws of gravitation and all that. And he became famous overnight, essentially. And so I got a couple of quotes here from guys just kind of reiterating the same thing that I just said. So this is from John Maddox, Nature magazine, the head editor, 1905. "Historically, the most dramatic proof that Einstein was on the right track with his general theory of relativity came in 1919, when Eddington and his associate Crommelin took themselves off to the western coast to track the total eclipse of the sun in that year. They were bent on measuring the predicted deflection of distant stars lying near the limb of the sun. And as the world knows, the prediction was confirmed within the limits of the accuracy of the observation. To general applause, Einstein became a celebrity overnight. To what is not so well remembered is that the measurements in 1919 were not particularly accurate. The standard error of measurement was roughly 30%, while the displacement of the images in the star field, or in the stars near the stars in the field near the sun of the gravitational field, ranged to half the deflection of that predicted. And later eclipse measurements have not been much better, largely because of the difficulties in making such accurate measurements from ad hoc observatories that have to be established." So yeah, they were pretty bad with the evidence put forward, and everyone just kind of accepted it. So earlier, when I was talking about plasma cosmologist leaving, so this is Edward Dowdy, who former NASA employee, like really smart guy. He went to Harvard, graduated, all that, really smart dude. And he started refuting relativity theory when he looked into this and found a similar situation, and that's why he became a plasma cosmologist. I have a couple of papers that he published here, and an interview that he did on Sky Scholar. If you go to Sky Scholar's channel on YouTube and type Edward Dowdy, you can watch his interview. It's a really interesting story about how he goes over the history of the starlight displacement and why he changed cosmologies. So when we conceptualize the starlight displacement, a lot of people think that like the starlight displacement happened in this vast gravitational field that's affecting things, because like when they show like the gravity well of the solar system, right, the gravity well of the sun's huge and all the planets are within that, right? So like so definitely starlight should be displaced, like not just exactly near the limb of the sun. It should be displaced like further out, like albeit less, but definitely to some degree, right? But no, only within this exact solar limb, right? So that's why they changed cosmologies. So let's see here. So gravitational redshift. So the Fraunhofer lines that he was talking about earlier, that's exactly what these are. So this is what he's talking about when they're breaking light into a spectrum and all that. So, Jeran, did you have any questions or anything
Nope, it's going well so far.
Was that?
Everything's good so far. No
Cool,
questions.
cool. Okay. Cool. So when they look out in space, they have different iterations of how they can interpret the redshift that they see, even though so you know how the scientific method would be like about isolating variables and all that controls and whatnot. So like they're just looking at the phenomenon and just deciding about like this much displacement or this much color displacement must be due to XYZ factors, right? So they have different types of redshift to interpret things. So they got Hubble shift, time dilation redshifts, which they call what is it, transverse Doppler effect or something like that. And then gravitational lensing, all that stuff. So when they get into the experimentation of some of this stuff, so in terms of gravitational redshift, right? So the Eddington observations was supposed to have spectroheliographed readings in tandem with those observations to back it up. So all this time from up until Eddington was 1919. So from 1919 from up until 1965 with Pound Repka, actually 1964, I think was the Pound Snyder. Pound Snyder was the first one. No, I'm sorry. Pound Repka was the first one. Anyway, so for about 40 years, they didn't have an actual mechanism or an experiment to prove the mechanism of their coordinate system to describe or to prove that gravity is interacting with light in this way and causing this spectra shift, causing the retardation of the frequency of light, right? So this experiment was conducted in like 1962, the Pound Repka experiment at the Harvard Jefferson Tower. What they had was a quote unquote photon emitter, and they were taking a known wavelength and shooting it down to the bottom of the tower and shooting it back up, and they were taking readings and seeing how much fringe displacement they were getting. Now, the ultimate conclusion of their experiment was inconclusive, so they did the experiment again. This time, it was called the Pound-Snyder experiment, and it was the same exact setup, just a straight tower up and down, and this time they just increased the height of it. So this one was 75 feet. The first one was 22 meters. So they increased it by just a little bit, did it again. So I'll just read their conclusions from their second paper, which was the same as their first paper, pretty much. So to quote from the men who did the experiment, it is not our purpose here to enter the many-sided discussion of the relationship between the effect under study of general relativity and energy conservation, and it is to be noted that no strictly relativistic concepts are involved in the description of the effects of the apparent weight of a photon as the apparent weight of a photon is suggestive. So their first paper was titled "The Apparent Weight of a Photon" because the way they were interpreting it was that light was falling to the ground, like it was catching a downward bias, so to speak. Like light was increasing in speed, and they didn't quite know how to interpret that because light is supposed to have the same speed, right? But based on the fringe shift change. So if the frequency changes, the speed would have to change as well. So they didn't quite know what to do with that. So that's what they're referencing there when they say the apparent weight is suggestive. And then they go on to say the velocity difference is predicted is identical to that of which a material object would acquire in free fall for a time equal to that of flight. So the time it took for the light to propagate from the 75-foot tower down to the bottom, they're saying that there was a speed increase. So the possibility a priori of the discrepancy between the simple theory and experiment in the dominion of the tenths, of a few tenths of 1% does not appear large. One aspect may be worthy that this does not include the general effect of Earth's rotation, which may reduce it, which I think they were trying to attribute the Sagnac effect a little bit to it, but they ended up not going with that. But I think they were just kind of throwing it out there as a possibility. Like maybe the Earth rotated a little bit under it. So then they go on to say, the view that the local time scale depends on gravitational potential appears to require a coherent source for confirmation. The present experiment is unable to distinguish the frequency change and velocity changes. For example, it appears for experimental comparison that the different potentials would make that a comparison of clocks at different potentials would make a useful complementary contribution to the overall status of the theory. So this experiment, Pound Repka and Pound Snyder, are put forward as experimental proof of a photon's interaction with the gravitational field in space-time curvature. As we just read here from quotes from the men who did the experiment, they were unable to distinguish between classical mechanic effects and relativistic effects. And they suggested that maybe an experiment like the Heffel and Keating experiment should be done. And the Heffel and Keating, which is the atomic clock experiment, where they took the planes going in different directions, and they were seeing how the clocks would go out of sync. And so no conclusive evidence, and this is, still right. So this was 1965 was their final published paper of their experiment. Let's see. So we have some various explanations that we could get into that relativists give to interpret the experiment as a relativistic effect. The big one that they go for is that they say that there is a time dilation effect, but if you calculate out time dilation and give them the best benefit of the doubt, the effects it's not even close. So like the Pound Repka experiment is 2.5 times 10 to the minus 15, and the time dilation effects, giving them the maximum benefit of the doubt to calculate it all out, come out to the effects of 2.17 by 10 to the negative 21. So it's not even close, or within the effect. It's not even within like the measurable precision of what they were doing to say that time dilation is responsible, or that this is proof of anything. Let's see. And some afterthoughts here. So some known effects about what could produce fringe or spectral shift in light like that, right? So there's this thing called the Stark effect and the Zeeman effect. The Stark effect is an electric field. When electromagnetic propagation goes through a field, the wavelengths get retarded proportionally to the density of the field and the direction of the current of the field, right? So and the same thing is true with a magnetic field, basically, and that effect is called the Zeeman effect. So light passing through a medium. So how we live in a giant magnetic field, or the block domain and all that sort of stuff, right? That's what we're kind of theorizing, right? So this magnetic field would facilitate like all the motion that goes on in the sky. It would facilitate that. Like it would show the same effects, right? Like the retarding of the wavelengths, they would be showing that, and having an actual phenomenon that they're observing, right? But they're not interpreting the actual effect of it, right? They're using relativistic effects to interpret it. They're saying, ignore these factors and just focus on the relativistic effects and stuff like that. So Ken Wheeler does an excellent demonstration of showing electromagnetic retardation, and he shows how you can show redshift and blue shift with the magnetic field. So what he has here is a ferrocell and a magnet. I'll play a little bit of the video. There's a ferrocell and a magnet, and what we see here is a redshift and blue shift when he moves the ferrocell over the magnetic field, and it causes the polarization and light changes when he does that. So, and we'll see an actual redshift blue shift mechanism change from a magnetic field. What you won't see is someone showing you a space-time experiment of space-time causing this, right?
I have motion and we have a phase.
So are you able to Are you able to hear the audio on this, Jeran?
Crankshaft and it's turning the magnet.
Yes.
Awesome. Okay, so I'll let it play out for a minute. I think it starts out at about 6 minutes, if I remember correctly.
Blue shift. If I move it away, let's just look at this one.
So looking at the magnet here, it's kind of hard to tell from the video. You can I can give you a link or whatever. You can look at it in the original quality. It's red shifted on this side on the north pole of the magnet, and on the southern pole it's blue shifted. The color spectrum is different, right? So when he moves ferrocell over it, you see due to the relative motion, you see the phase
One
shift.
pole only. Let's ignore this pole over here, okay? You notice that this redshifted now? Let me move this closer to a person over here. Let's say there's a person on a little planet over here, and this is a star. Okay, now it's redshifted. Let's move the star closer to this person over here. You see how this blue shifted? Let's move it away and watch this blue, which is bluish green, but it's still blue shifted, turn to red. Red shift. Blue shift. We're only looking at this pole over here. A second. I think I had a little power outage there. There we go. Blue shift. Red shift. Red shift, moving away from this relative point. Now let's take a look. Let me check my power connection here. Let's take a look at the other pole. Hold on a second. There we go. Sorry about that. Let's take a look at the other pole over here on the right side. Let's orientate my magnet exactly. Okay, let's wait for it to appear. There we go. Let's take only a look at this. Blue shift relative to this person over here. Let's say this point over here. Blue shift, as it moves away relative to this point, we have red shift. You notice how it shifted to the red? Now watch it shift again. Remember, only looking at this pole on the right side of my finger. Okay? Red shift, blue shift. Red shift, blue shift. Inverse to the other pole. Look closely. Nothing has changed other than disparity of EM retardation. It has nothing to do with space. Has nothing to do with time. It is EM phase shift disparity, or EM retardation. This is also the differential that is programmed into every global positioning satellite relative to its motion. This has nothing to do with Einstein, has nothing to do with general relativity, and has nothing to do with quantum mechanics. The universe is purely dielectric and magnetic. If you want to think of it as electrical, that's fine. Electricity is phi times psi, Q and Planck of electrification. Electricity is a hybrid.
All right. So that was Ken Wheeler demonstrating redshift and light, facilitating it that way. Oops, I think I ended the whole screen share. 1 second. We got 6 minutes left on the hour, Jeran, if you want to just go ahead and wrap it up there with that. Or we can close out on that.
Whatever you want to do. No, my mic.
Okay, yeah. So I'll wrap it up with that. Let's see here. So we'll close it out with that. So tomorrow night I'm actually doing this full presentation again, and a longer rendition of it, going into even more detail. So you can catch it tomorrow if you want more. But basically, I continue to go on through all the classical proofs that they give for general and special relativity, and just dismantle them one by one. So like when you go to Wikipedia and you type in proof of relativity theory and you see the list there, your boy goes through all of them and dismantles them. So you can check that out tomorrow at 10 p.m. EST.
Awesome. Thank you very much for that. And that's helpful. And now I got to turn this volume down again. Is that any better? A little better for me. You can still hear me okay?
Yep.
Okay. Just trying to get this worked out. All right. So we're going to let you guys jump on the show if you want. We're going to go over to Rockfin, though, for the final hour. Take your guys' calls from there. And let me just check and make sure there's no thank yous or anything we need to say on this side. And we'll be heading over there. So I will drop the link in the chat. Let me just check something really quickly. And then I'll be able to go back after the show and listen to different changes I was making in the sound to see if anything's better for you guys. Let's go with super, see if there's any super chats. We've got a few of them. It looks like we've got, let me bring these up. We've got Eric with 3 super chats. Thank you very much, Eric. And I believe that is, yeah, all of our super chats come from him. $5 says, hello, tap, tap. Is this thing working? It is working. Then he says, thank you, Alan. And then he says, Flattoberfest 23, new show, debatism, FE app, update, friends, profile, chat groups, airship, South Beyond. There you go. All those things. Yeah, so check out Tuesday. I've got debatism again, second edition. Hopefully it goes better. Learning as we go. I changed some of the rules already. And on Tuesday, we've got Brenda debates versus Pitch Lumen, or Nathan Erickson, if you will, on the flat Earth. But this time the rules have changed. We're now requiring, rather than topics, it will be claims. So each person will bring 5 claims to the show, and they'll make a claim and then have to back it with evidence, and then the other person will have the opportunity to refute that, or to dismantle it, or to agree, as might be the case sometimes. But it'll be good. By the end of the debate, in just 90 minutes, you will have heard 10 different claims made, 5 on each side, backed by evidence, and then you can decide for yourself which one is being honest, which one seems to be sound evidence and backed by evidence, and which one seems fallacious. So that is coming on Tuesday night, 6 p.m. Pacific. Please be here for that. That'll be on my channel, of course. I think that's all I need to say for this side. All right, I'm going to grab the Rockfin link.
Hey, speaking of debatism, real quick, I put a link in the chat. So I have an open challenge out for a debate as well.
Okay.
So if anyone wants to help find me an opponent, just put it out there. And this is to be hosted on Debatism as well.
Awesome. What do you want to debate? What topics?
So it'll be on the observational evidence supporting relativity theory and the substantiation of Earth's orbital speed. So basically heliocentrism versus geocentrism and the main supporting theories that support it, right? And a justification for abandoning the etheric framework. So that's the layout I got. So I'll read the preface here. So position preface: throughout the history of interferometric experimentation, the speed of light has been shown to vary without experimental evidence for the invariance of C. The second order corrections of length contraction and time dilation become unjustified. Consequently, without that justification, to accept Einstein's postulates and Lorentz transformations, the qualitative mechanism to explain the experimentally measured difference between heliocentrism and geocentrism vanishes completely. By way of reductio ad absurdum, the natural interpretation is that the Earth is stationary with respect to an ether wind, and then I'll substantiate those claims by dismantling relativity theory, which is the preferred interpretation of how they get Earth's orbital velocity and all that, right? So just kind of attack it from that method.
Excelente. And yeah, you can go to jeranism.com/debate, and you'll see there's just a couple Q&As here, but one of them is, I'm ready to debate, but don't have an opponent. So just reach out to me and tell me what you want to debate topic, and I'll try and find you one. If you already have an opponent, reach out to me and we can get you scheduled. And then it says here, I'm looking for somebody to debate what topics. So far I just got a couple people here and who have reached out. Chris wants to debate the flat earth model. He's a flat earther who wants to debate the current flat earth model. He wants to argue against the AE model. McToon is looking for somebody to debate over 5G. Rufy, who I believe is Rufus, is open to debate celestial navigation, measuring drop due to curvature, long distance observations, flight routes. And so I'll just keep adding people in here. So like, for instance, I'll add Alan in there. And so if you want to reach out to me, you can t.me/Jeranism and just say, hey, I want to debate this. And we've got a lot of people who signed up yesterday too that I haven't added to this list yet. So it's going to take off. I might even put it on its own channel. We'll see what happens. I want to make sure we get a good layout done, a good kind of, because I do want to keep them 90 minutes or less. So even if that means me having to be extremely punctual as far as the time clock goes, we will see. So don't get your hopes up too high for a perfect show on Tuesday. It probably won't be. It'll probably be another test to see if the time periods are right and whether I need to add time somewhere, remove time elsewhere. So it's a thing in the process, in the works. But in the end, what it should be is a place where you can go and you can get people making actual claims, which is a lot better than topics. When I called it topics, which is kind of the same idea, but the problem is that topics could be, let's talk about the weather, and it's just not there's nothing there. There's no substance. When you make people make claims, now people are debating and they're actually saying, I believe this and here's my evidence for it. And the other person saying, well, I don't believe this and here's why I don't agree with your evidence. And then it's up to you to decide which one you think presented their case better. Also, we have a interesting show coming up in a few weeks. There's a fence sitter who wants to come on the show and wants to hear presentations from both sides about their best evidence, and then we'll make up his mind or something based on that shows, so he says. But we'll see. But I think it's a good idea to have him. He has questions. He has things he's heard from both sides that he now thinks are lies that he wants to bring up. Why does Glober say this? Why does Flat Earth say this? If he's finding them not to be true. So I think that'll be an interesting show as well. All right, let's go over to the Fin. We are going to copy this link. I will be putting it in the YouTube chat. And thank you guys for being here on YouTube. Much appreciated. Let me paste that. And we'll be over at the Fin. Okay, let's see here. Spherical Cow says debates are useless. Well, yes, as far as changing somebody's opinion, but if you think debates are useless, I don't think you've been paying attention. There's quite a few people who have made the move because of a debate or some form of it. Nobody's going to change their mind in that moment. It's just not how it's supposed to happen. But I think that people do watch debates, and if they can actually follow along with it, they can actually make decisions on it. I think if a debate's 4 hours, no. It's just, or there's too much fighting, or there's not enough moderation. There's a lot of things that can lead a debate to be useless, but I think they can be helpful, especially when you make people give claims. The Globe Earth claims to be so factual, so they should be able to give claims backed by evidence, and we shall see how that goes. We shall see. Should be interessante. All right, here's the links in there. We'll see you guys on the Fin, where all the cool kids hang out. You're exactly right, Benny Boy. And then we'll let you guys jump on the show. So come on over there. We will see you shortly. Till then, peace. Thanks so much. Later. Bye. Signing off. All that fun stuff. Make sure you're doing all right. Okay.